Decision-making under uncertainty. If there was no uncertainty, we'd know what decision to make, but randomness is going to enter in here, and we're going to have to take care of it. What I'd like you to think about in terms of decision theory is think of a decision being a game between two people, you and an opponent. And the opponent takes a stand, and you take a stand, and then you both find out what stands you took, and there's a payoff because you've done something and she's done something. So you've got a payoff because of the positions you've taken. That's the way you would think of a decision process, a decision mechanism. And if you got that in mind, the rest stuff's not going to be hard at all. Now, like in all other fields of statistics, we have to start with jargon. States of nature. What states of nature are simply our opponent's decisions or actions. It started out with our opponent being nature itself, and therefore rain and things like that were the opponent's decisions, and nature was deciding whether it should rain or not. But we use decision theory when our opponent may be a business opponent or another football team or something. Has nothing to do with nature, yet we still use the words state of nature when we refer to our opponent's decision. So a state of nature is just a decision, but it's a decision by our opponent, not us. Examples of states of nature: rain. Now rain, snow, sleet, hail, sunshine, they're all really states of nature. But we sort of imagine that nature has decided to make it rain. That's nature's decision. How about the price of a stock? Well, now nature's not involved. It's the body of economic systems going on. All the other people in the stock market compete with each other, and that causes the price of a stock to be what it is. Well, so although it's not nature, it's sort of a semi-natural thing having nothing to do with a particular opponent. However, what about the next play in a game? We're a coach of a football team, and we have to tell our players what to protect against. The other team's got the ball. So you say, well, let's think now. Is he going to run? If so, we'll protect against the run. Is he going to pass? We'll protect against the pass. So the defensive play depends on what we think he's going to do. What the opponent's going to do is the state of nature. The next play is the state of nature of our opponent. Okay, let's get on. Decisions. When we say decisions in decision theory, what we're really referring to is our decisions, our possible decisions. What can we do? What are the things we can do? So decisions by itself refers to us and our decisions. Examples: take an umbrella. If nature could make it rain or not rain or snow or sleet, one of our possible decisions would be to take an umbrella. If we're talking about the stock market, we wonder whether it's going to go up or down. Nature can make it go up or down. We can decide to buy 100 shares of stock, or sell stock, or buy 50 of this and 20 of that. We make decision about what to buy. Nature makes decision about what to do with the stock market prices. Prepare for a pass. That might be our decision. If the opponent was to either do a run or a pass, we have to protect against something. We might decide to prepare for a pass. That would be our decision. Now, what we do with those things is we take the decisions and states of nature, and we say, okay, now uncover them. What is the payoff when we see what our opponent does and what we do? This value of each decision and each state of nature, the combination of those, is called a utility. And we write the function U, the decision and a state of nature. So it's a function of both what we do and what the opponent does. Don't let the formula worry. It's easier to think in terms of a utility table. Let's put the data, all we've done so far, in a utility table. And it looks like that. And what it is we take the states of nature, the possible decisions our opponent can make, and we write them in across the top of the table. In this example, there are 6 possible things that nature can do to us. Then we write along the side our decisions. What are the possible things we can decide? Of course, in a real situation, there may be many more than that. In real-life situations, nature can do many things, and we can decide many things, most of which we're not interested in, we know are not worthwhile, so we'll get rid of them right away. And some nature decisions are irrelevant, we throw them away. But for each decision and each state of nature, there's a utility, a value to us, a payoff. That utility is a function of the decision line you're on, D3 in this case, and the state of nature line you're on, S2. So each entry depends on what decision and what state of nature. And there'll be a number in here, a payoff to us. Might be positive, might be negative. If we lose money, it'll be negative. Gain money, it's positive. And sometimes the utility table is extremely difficult to write in because we talk about things which aren't money at all. If it costs $20 to take a tuberculosis test, okay, I would have to somehow weigh $20 against, if I don't take the test, I won't find out that I have tuberculosis. Well, what's going to cost me then? I somehow have to figure out what's the total cost of my not checking the disease if I have it. So I have to relate money to things which are health. And that's extremely difficult to do. We have to sit down and say, well, what's it worth to me if? And sometimes those things are not easy. But let's assume we can do that. We can write down numbers into our utility table. And then we end up with a utility table of this form. Well, we can't do anything yet. We have a decision under uncertainty. What does uncertainty mean? Where does it come in? If we knew which state of nature would occur, we could pick the decision which would give us the largest utility or gain. And what does that mean? Well, if here we are, and we happen to know that that's what our opponent's going to do. Well, if that's what our opponent's going to do, we can sort of get rid of everything else in the table and look at only these numbers. Now, we look at these numbers, it's like going to a buffet table. You look at all the stuff on the buffet table, and you're only allowed to eat one thing. Which do you pick? You pick the one which is best, the one you like best. And I didn't say best for you, the one you like best. Maybe this is the one. Well, what do you mean by best? It means it's the largest payoff. So you'd make the decision which gave you the largest payoff if you knew which state of nature it was. There's no real problem there. There's no problem if you don't have uncertainty. However, when we have uncertainty, we don't know which state of nature. And it's very possible that for this state of nature, that's the best thing to do. For this state of nature, that's the best to do. For this state of nature, that's the best. For this state of nature, that's the best. For this state of nature, maybe that's the best. So there's no sure decision to make when we don't know the state of nature. Okay? All right, we're uncertain about which state of nature will occur. So, what do? Well, we realize that the state of nature is a random variable. What is a random variable? When we don't know, we can't predict something, it's random, okay? The state of nature, we can't predict it. It's random. It's a random variable to us. We have to obtain probabilities for the states of nature. If they're random variables, they have probabilities. What are these probabilities? Oh, that's going to be hard, but I do the best I can. They're going to be usually personal probabilities. What do I think's going to happen? How much do I believe? What does my belief say that the opposing team is going to run for a pass? I might be able to work that out. I might look at the footage of the team plays and say, gee, he runs a pass 40% of the time, 60% of the time he keeps it on the ground. Therefore, the probability of being on the ground is 60%. The probability of throwing a pass is 40%. That wouldn't be hard at all. But usually, it's a difficult case of the weather. The weatherman says 30% chance of rain. If you believe him, you would use 30% in there. Personally, I never believed the weatherman. He's so rarely been right. However, you've got to have a probability somewhere, so you might take that 30% and say, gee, he's a little optimistic always, so when he says it's going to rain with 30% chance, it pours here, so I'm going to up that to 40%. And you might adjust the probability till you get a probability that you can believe in, a probability that you think is correct. It will, of course, be a personal probability. Okay, let's look at the utility table. When we have these probabilities, they are associated with the states of nature. Each state of nature has a probability associated with it. That's very important. Many people make the mistake of thinking that the probability is associated with the decisions. Of course they're not. The decisions are ours to make. We make a decision. We have absolute control over what decision we make. There's no randomness involved. It's a choice. Here, we don't know what the state of nature is. Of course, our opponent knows, but we're not the opponent. We have to guess, and we put probabilities on the states of nature. You may not be able to read this. This says probability of state 1, probability of state 2, probability of state 3, and so on. That's what's happening here. So these are the probabilities. And I want to point out, note, uncertainty is associated with the states of nature, not with our decisions. Remember that. That's a mistake people make all the time, and there's no reason for it. What do? Well, we find the expected utility. That's what we always do, average things up, the expected utility. For each decision, there is a long-run average or expectation. This is the expected utility. And here's the formula for it. It's usual. You take formula for utility is the sum of x, p of x. Remember that? Well, state of nature, multiply it by the utility of that state of nature for this decision. See, we're looking at a particular decision, protect against the pass. We look at that decision and we find for each state of nature there's a utility relative to that decision. Multiply it by the probability of happening, and you sum them up and you get the expected value. Well, let me go to a picture. Picture's worth 1,000 words. Here's what's happening. I have, you might not be able to see it very clearly, but I have the probability associated with this state of nature. The probability associated with this one, the probability is associated with the states of nature. So I have probabilities. I also have utilities, which are essentially x's. Now, if I want the utility, the expected utility, the average utility, the long-run average utility for this decision, I would take this, multiply it by this, plus this multiplied by that, plus this multiplied by that, plus. I would multiply these and sum them up, and I would get the expected utility for this decision, and I would write that down. Now I go to this decision and multiply the probability by the utility. Multiply the utilities in that row by the probabilities of each state of nature. And I'd sum those up, and that would be the expected utility if I made this decision. If I make this decision, here are my utilities. Here are the probabilities of those utilities. So I weight the decision with the probabilities, add them up. Do that for each decision, and I get a list of expected utilities, one for each decision. Which decision should I pick? Clearly, I should pick the decision which is biggest. The expected utility is biggest. Okay, so let's say this one gave me the biggest number. That's the decision I should make, the one which affords the largest expected utility. The Bayes decision, and this is named after Mr. Bayes, not because he discovered it, because we liked them. Oh, statisticians liked them. I wasn't around when the name was given, but it was named after Mr. Bayes, and that's the decision which affords us the largest expected utility. The actual Bayes utility, the largest utility, is called the Bayes utility. So the largest expected utility, the largest number down the side, is called the Bayes utility. And the decision which gives us that Bayes utility is called the Bayes decision. And what should we do? The optimal thing to do is to pick the Bayes decision. And in the long run, we will obtain the average. Of course, we're not going to get the long run, but at least that's our expectation. Okay, we have all the ingredients. Now let's do an example and see if we can't make some money with it. Okay? So here's an example. We can invest $100 in stock A. That's one of our decisions. We can invest $100 in stock B. That's another of our decisions. We can invest $50 in each stock A and B. That's a third decision. Or we don't have to invest at all, just keep the money in our pocket. And that's a fourth possible decision. What are the states of nature? Well, we'll simplify this. Let's say stock A can go up or down 2%. And stock B can go up or down 4%. That's the four states of nature, because one can go up and the other can go down and vice versa. So there are four states of nature. Now, what are the probabilities associated with these things? Well, at this point, I don't know anything, so let me say they're equally likely. Because I don't know anything at all, I'm just going to say, well, equally likely for the moment. Okay? And now I have to write out my utility table. And what I do is I have states of nature on the top, and the four possible states of nature. A can go up, B can go up. A can go up, B can go down. A can go down, B can go down. A can go down, B can go up. A can go down, B can go down. tongue twister. I can put everything in A, I can put everything in B, I can put $50 in A and 50 in B, or I could not invest at all. Of course, if I don't invest at all, I don't win or lose anything, so I'll write 0 for that. Don't win or lose anything if I don't put any money in. But if I put $100 in, and A goes up, I don't care what happens to B because I only invested in A. A goes up, it's now worth $102, I'll put down my profit in here. I made $2 on the deal. If I invest $100 and A goes up and B goes down, well, I don't care what happens to B. A went up and I got $2 because now my stock's worth $102. If I invest in A and A goes down and B goes up, I lost $2 because A went down to $98. If I invest and A goes down, I don't care about B, I still lost $2. If I invested in B, A and B go up, I gained $4 because B goes up 4%, $4. If I invest in B, I don't care about A, B goes down, I lost $4. Invest in B, B goes up, gained $4, B goes down, lost $4. What if I put $50 in each of A and B? Well, A and B go up, so I get $2 on my $50 from the stock I put in A, and I get $1 from the stock I put in A because $50 went up 2%, and I get $2 from the investment in B because it went up 4%. 4% of $50 is 2. Total profit is $3. If A goes up and B goes down, I made $1 because A went up, but I lost $2 when B went down. Negative $1. If A goes down and B goes up, well, B went up, I made $2, but A went down, I lost $1, I ended up with $1 profit. If I invest in both and A goes down and B goes down, well, I lose $3. $1 I lost on my A stock, and $2 I lost on my B stock. Now, what decision should I make? Well, I have to find the expected utility. So I take 25%, since I said they were equally likely, 25% of these numbers, and I get 0. 25% each of these numbers, I get 0. 25% each of these numbers, I get 0. Of course, I get 0 here. They're all the same. What decision should I make? Well, this is a fair game. I can't win or lose. I can do anything. It's just an even bet here. Well, that's what happened because, actually, it happened in this case because I didn't know anything about what's going to happen to the stock. And so what I do is I call up a friend, stockbroker, and say, hey, what do you think is going to happen to stock A and B? What's your opinion? He said, what's the scuttlebutt? What do you hear? Got any inside information? Got anything I should know that I don't know already? And I hear all the things about, oh, A is merging with something, and B just had a layoff, and I find out these things. And then I come up with other probabilities. And what I hear tells me that the probabilities aren't equally likely, as I thought, but in reality, there's a 30% chance that A and B will both go up. 25% chance A will go up, B will go down. 20% chance A will go down and B will go up. And a 25% chance A will go down and B will go down. So I've changed my assessment of the probabilities. That's all I've changed. The utility table is exactly the same. But when I multiply these probabilities by the numbers, I now get 0.2 here. And if I multiply these probabilities by these numbers, I get still nothing here. And if I multiply these probabilities by these numbers, I get 0.1. And of course, this gives me 0. Now, I have a difference. And I can decide on something. And I look at this and I say, if I decide decision A, I will make the most profit in this. My expected utility will be higher than my expectation if I do anything else. Since it's highest for decision A, this is the Bayes utility, 0.2, and the Bayes decision is A, and that's what I should do. I should decide A, do A, that is, invest $100 in stock A. Okay? That's how decision theory works. Decision theory is designed to emulate the way people think, the way people actually do decisions. And it makes a mathematical procedure for the thinking process. And if you go along with that, if you believe it, I do, then you can actually improve your chances of making a better decision. I hope it turns out to be useful for you.